Greetings and welcome to the series of lectures on exponential and logarithmic functions. In this lecture, we'll discuss exponential functions. So, it's a little bit difficult to figure out what an exponential function looks like. So consider a bouncing ball, and you just drop the ball, and the first bounce, it hits the ground, and it bounces back up because it's a bouncy ball. But it doesn't go as high as where you dropped it. Okay, let's say it only goes 2/3 of the original height. And then it hits the ground again, and it bounces back up. But this time, again, it only goes 2/3 of the height of the previous bounce. And it continues and continues and continues until eventually it stops bouncing. In essence, what we're doing is creating an exponential function. The first bounce is just the original height. The second bounce would be 2/3 of the original height. The third bounce, when it's up in the air before it hits the ground, it's 2/3 of the 2/3 of the height. So it's 2/3 of the previous bounce, but that was 2/3 of the previous bounce. The next bounce, when it's up in the air, would be 2/3 of the previous bounce, but that's 2/3 of the previous bounce, which is 2/3 of the previous bounce. So in essence, for every bounce, we're multiplying it by 2/3. So let's figure out how we can work this out for any of the bounces that we want to know. The initial height, let's just say it's 1 meter. So for the first bounce, okay, we hit the ground and we pop back up in the air. It's going to be height times the 2/3, which is 2/3. So it's 2/3 of a meter. For bounce 2, the height is going to equal the 2/3 times the previous bounce, which is 2/3. In other words, 2/3 squared. For the third bounce, it's going to be 2/3 times the previous bounce, which is 2/3 square. So it's 2/3 cubed. For the fourth bounce, 2/3 times the previous bounce, which was 2/3 cubed, so that's 2/3 to the fourth. If you notice, the number of bounce will be the power of what we're multiplying it to, the exponent. We can even write this initial height as 2/3 to the 0. Right? So our formula will hold. So for any bounce, any nth number of bounces, our height is going to be 2/3 times 2/3 n minus 1. In other words, 2/3 n, because n minus 1 was the previous height of the bounce, so 2/3 n. And as the number of bounces gets higher and higher and higher, this fraction gets smaller and smaller and smaller until eventually the ball is not bouncing at all. We'll reach a point to where there's only so many bounces because, well, gravity takes over. And therefore the ball has to stop bouncing sometime. So we do have a definition. We've already seen that 2/3 to the n is actually written in exponential it's an exponential function, meaning that an exponential function is any function that can be written in this form, where f of x, the function, equals b to the x. B must be greater than 1. Okay. Here are some examples. F of x equals 2 to the x. Y equals 3 to the x. And you're saying, well, how can it be y? Well, we can say that f of x equals y. So we're okay with y. Or f of x equals 1/4 to the x. All of them to the power of x. So they are in exponential form. All right, let's see an example of exponential functions, and we'll just say we have f and g. And f is defined as f of x equals 2 to the x. And g of x is defined as g of x equals 3 to the x. And we're going to figure out all of these different values. So f of 0 would equal 2 to the 0, and 2 to the 0 is 1. F of 1 would equal 2 to the first, which is 2. Plugging in wherever I see an x, I got to plug in what the value they're giving me. F of 2 will be 2 to the second, in other words, 4. F of 3 will be 2 cubed, in other words, 8. F of negative 1 is 2 to the negative 1, which is 1 over 2 to the first, which is 1/2. When we need to change the exponent from negative to positive, remember we cross that fraction bar. All right, 2 to the negative 2 will equal 1 over 2 squared, which is 1 over 4, 1/4. And then we'll do one more. F of negative 3 is going to be 2 to the negative 3, which is 1 over 2 cubed, in other words, 1/8. So let's try these out for g of x. So g of 0 will be 3 to the 0, in other words, 1. G of 1 will equal 3 to the first, which is 3. G of 2 is 3 squared, in other words, 9. G of 3 is 3 cubed, which is 27. G of negative 1 is going to be 3 to the negative first, which is 1 over 3 to the first, in other words, 1/3. G to the negative 2 is 3 to the negative 2, 1 over 3 squared, 1/9. Okay, we need to simplify it as much as we can get. And then finally, 3 to the negative 3 is going to be 1 over 3 cubed, or 1 over 27. That's how we're going to work exponential functions. It's just like any other function. We're going to plug in the value which they tell us to plug in, and we're going to evaluate it. All right, sometimes when you go to the doctors, they need to inject you with iodine 131. I believe it's a chemical that when you take an x-ray that it lights up your body so they can see it. But the chemical doesn't go away immediately. It actually has a half-life of 8 days, meaning whatever the amount they inject you in, the chemical breaks down, half of the chemical will break down in 8 days. And there is a formula. The amount at a specific time is the original amount times 2 to the negative t over 8. This is an exponential function. So we want to figure out if a patient is given 1,200 micrograms dose of iodine 131, how much iodine 131 is in the patient's system after 10 days. And then we want to figure out what will it be after 16 days. All right, so the first one is A of 10, meaning our original amount, A of 0, would be the 1,200 micrograms that the patient was given, times 2 to the negative 10 over 8. Negative 10 over 8. Right? So A of 10 will equal, well, that's 1,200 still, times the 2, and we can reduce this down into negative. 8 goes into that one time with 2 left over. So 1.0, let's see, I got to do that math. 8 into 10 is 1. 20, that's going to be 2. And that will be 4 is 5. Okay, 1.25. Now this is a calculator problem, right, from here on out, but let me just go ahead and show you the work that I've done. So once you plug it into the calculator, it's approximately 504.5 micrograms left in the system, in the body of the patient. That's the system we're talking about. Right. All right, so let's try 16 days. So A of 16 will equal the original amount still, 1,200, times 2 to the negative 16 over 8. Well, 16 over 8 is 2, so A of 16 will equal the original amount, the 1,200, times 2 to the negative 2. But 2 to the negative 2, I don't even need a calculator for this one. 1200 times 1 over 2 squared. And 1 over 2 squared is 1/4. So a to the 16 will equal 1200 times 1/4. Push it up a little bit. And that will equal 1200 divided by 4, which is 300 micrograms. Will be left in the system of the patient at the end of 16 days. And we can continue and continue and continue until if we get down to 0 micrograms, then the chemical is completely gone from a person's body. So if at 8 days or at 10 days they were 504, so let me write that down here, 504.5 micrograms, and after 16 it went down by about 200. We could probably expect that after another 600 or 6 days, it probably has, again, maybe cut in half, and cut in half, and cut in half. So we're looking at maybe a month before it's completely out of the system. I'll leave that problem to you to do, to figure out how many days it would take for the whole entire amount to get out of the system. All right? Now, I'm not going to necessarily walk you through how to graph an exponential function, but it's basically the same way as graphing a line. We're going to choose a value for x, plug it in our function, and find the corresponding value of y. So if we want to graph y equals 2x, 2 to the x, I'm being very careful how I say this, 2 to the x, then what I need to do is wherever I see, I'm just going to select some values. Right? I'm going to determine what values of x, so I'm going to choose -3, -2, -1, 0, 1, 2, 3. Kind of pick easy ones for me. Plug in y, 2 to the -3, well that's 1 over 2 cubed, which is 1/8. So the corresponding value of -3 is going to be 1/8. And you continue this, so -2, it will be 1/4, the math is laid out there for you. -1 is 1/2. 0 is 1. 1 will be 2. 2 is 4, because 2 squared is 4. And 3 is 8, because 2 cubed is 8. These are points that I can plot. I'm going to plot the easier ones first, right on top of what I have right now. 0, 1 is right there. 1, 2 is 1 over and 2 up. 2, 4 is 2 over and 4 up. And 3, 8 is 3 over and 8 up. And you can start to see the shape coming through. Now the fractions are a little bit harder. You just kind of have to guess. So -1, so I go 1 to the left and up 1/2. -2 1/4 is going to go to 2 to the left and up just a little bit. And then -3 and 1/8 is go over left 3 and up just a little itty bitty bit. From there you should be able to see the shape of the graph, and no, I'm not going to graph it over my red line that I already have, but that is the shape of an exponential function. Now, I do want to say, the graph will approach the x-axis, but it won't touch it. There is no value of y that will produce a 0, because any positive exponent will make this thing grow bigger, 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 bigger. Any negative exponent will just make it go closer and closer and closer and get smaller and smaller and smaller, but it will never be 0. There's no x value that will force that value to be 0. It will come really super close, but it never meets 0. So that's the concept of just kind of looking at it logically. The bigger the value of x, the bigger the value of y. The smaller, more negative the x, the smaller value of y, but it will never be 0. Hence, approaching the x-axis, but never reaching it. Now let's go ahead and graph one more. Again, I'm not going to work through all of the details. I'll let you do that on your own. But here we have a graph of y equals 1/3 to the x. So again, I'm going to give myself some x values, and I like -3, -2, -1, 0, 1, 2, 3. You can choose whatever values you want, but these are the ones I'm going to choose. And for each value, I'm going to plug into x. And I'll do the first couple ones. Y equals 1/3 to the -3. Since it's a negative exponent, I need to, in essence, take the reciprocal of what I'm looking at and change my exponent to a positive. So it's 3 cubed, and 3 cubed is 27. The second one, y equals 1/3 to the -2. Again, I'm going to take the reciprocal of 1/3. That will make my exponent positive, and I have 3 squared, which is 9. Y equals -1, or x equals -1, therefore y equals 1/3 to the -1. In other words, 3 to the first, which is 3. Let's plug in 0. Y equals 1/3 to the 0. Well, that's 1. Plug in 1, we're going to get 1/3. Plug in 2, we get 1/9. And plug in 3, we get 1/27. Right? 1/3 to the third is 1 cubed over 3 cubed, which is 1/27. Now again, we're going to just use these points that we found to plot our graph. So -327 is really high up there. Can't even plot it right now. 2, -2 and 9. It's going to be right there. -1 and 3. You just want to give yourself enough points to see the shape forming of your graph. 0 and 1. 1 and 1/3. 2 and 1/9. And as you see, we're getting really super close, and we can graph our graph. So this is the graph of y equals 1/3 to the x. Again, we will never touch the x-axis, but we get really, really close, and we will shoot out to infinity here, or towards infinity. To infinity and beyond, right? All right. So here's kind of a cool thing about exponential functions. We have families of exponential functions. For example, y equals 2 to the x, y equals 3 to the x, y equals 4 to the x. So in essence, the larger the number that I'm raising to the power, the faster my growth is. So if this was 1 to the x, then I'm growing very, very, very relatively slowly. But 2 to the x is my green line. That's growing pretty fast. 3 to the x is growing a little bit faster. 4 to the x is growing even faster, and you can imagine 5 to the x is growing faster. The closer, or the larger our number gets, the faster it grows. Now, thinking of that same type of idea for fractions. My fraction is growing smaller at a slower rate when my fraction is larger. I know it kind of makes weird sense. It's a little bit backwards. If my fraction is larger, it takes a little bit more time to grow smaller, right? Because we're reaching 0. We never get there, but we're reaching 0. So 1/2 is larger than 1/3, so it takes us a little bit longer. We're a little bit higher here, but we will eventually get there. 1/3 is smaller than 1/2, so it gets there a little bit faster. And 1/4, you see, we dip down pretty quickly here to get down to 0. So we get smaller faster because we started out as a smaller number. So it didn't take us as long to get to really super close to 0. So these are families of exponential functions. And if you kind of know one, you know what you're looking for when you're graphing a very similar family cousin to what you know. So if you're real familiar with 2 to the x and what it looks like, then you would know 15 to the x is really, really tight. versus 1.5 is a little fatter, right? It's going to be out here because it takes a little bit, it's a little bit slower in the growth than 2 because it's a little bit smaller, right? And then with fractions, if you know what a general fraction looks like, then you should be able to figure out, is it really, really close? The smaller the fraction, the closer to 0 it's going to get on the y-axis. If it's bigger, like 3/4, it's going to be on the other side of this 1/2 because 3/4 is larger. So it's not going to start out as steep, but it does eventually get down to really close to 0. So those are families of exponential functions. Probably in a previous class, you've dealt with compound interest. So I'm not going to go through all the details of it, but I will say what all the parts and pieces are. Here's the formula. A of t, meaning we're dealing with time, will be the principal times 1 plus the rate over the number of payments per year, all raised to the number of payments per year times the amount of years. So P is principal, that's the amount of money that you put away. R is the interest rate, annual interest rate. N is the number of times per year that it's compounded. And T is the number of years that you put it away for. So let's take a peek at an example. Now we're going to use this formula in 2 ways. The first is, if we deposit $500 at 8% interest compounded quarterly, how much will be in the account after 5 years? The second way we're going to use this formula is we're going to try and figure out if I get, I'm still depositing the $500, but how long will it take to have $1,000 in the account? So let's do the first one. The first one is going to be A of 5 because we have 5 years. We put away $500, so our principal is $500. 1 plus our interest rate is 8%, 0.08. The number of times it's compounded quarterly, so that means 4 times a year. N is 4. All to the 4 times t, and t is 5. Okay. So now that we have all that information, let me switch it up and start working on this problem. All right. A of 5 is going to equal the $500. 1 plus, well, 4 goes into 0.08, 0.02 times, and 4 times 5 is 20, just simplifying as quickly as I can. A5 will equal 500 times 1 plus the 0.2, so it's 1.02, all to the 20th. This is a calculator problem. Okay, so let's see, let me get my fancy-dancy calculator phone here. And put it on scientific mode so I can do the power. All right, so I have 500 times 1.02, all raised to the 20th power. So it's 742.97, blah, 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 blah. This is money, right? We invested money, so we better make sure that we round this to the nearest penny. And if I round this to the nearest penny, the amount in the account in 5 years is approximately $742.97. Right? So I rounded to the nearest penny. Looked at the 3. 3 is less than 5, so I just chopped everything off there and kept the 7. All right, so that was the first part of the question. The second part of the question was, how long will it take to accrue $1,000 in the account? Well, we can see after 5 years, we would have $742.97. So we want to know how long will it take to get $1,000 in the account. So my amount is 1,000. My principal is still 500. I'm going to go ahead and skip to the 1.02 because all of that is exactly the same. So it's 1 plus 0.08 over 4. And that reduces down to 0.02, and then that adds up to 1.02. So I'm skipping some steps because I already did the work. My n was 4, but I don't know the amount of time that it's going to take. All right, so there's a couple things that I can do here to try and solve for t. 500, let's divide each side by 500. That means 2 equals 1.02 to the 4t. Okay, so here's what we're going to do. We're going to try and figure this out. I'm going to give some values of t's, and then we're going to figure out what 1.02 4t will equal. I don't know. There's no magic way of plugging this into the calculator. So I can get pretty close. I do know that if it was 5, then it's not quite the right amount, but I know I'm fairly close because if it was 5 years, I would have the $742. So let me go ahead and say, try and keep this on the screen so you can see what I'm doing. 1.02 times, well, t is 5, so 4 times 5 is 20. So that's approximately 1.486. All right, so we know we need a little bit higher number of t. So I'm going to try 10 when t is 10. So that means that's 1.02 to the 40th because 10 times 4 is 40. And that gives me 2.208. That's too much. I'm looking for it to equal 2. So I'm narrowing it in. It's somewhere between 5 years and 10 years. So I'm going to try, I don't know, let's try 8 years. 1.02, 8 times 4 is 32. Ah, we're getting closer. 1.00 or 1.885 we'll round it to. So it does look like it's in between 8 and 10 because 1.8 2 is in between 1.8 and 2.2. So let's try 9. 1.02, 9 times 4 is 36. All right, 2.0398, so I'm rounding that to actually 4. That's really darn close. So the time it would take is approximately when t equals 9, we will have $1,000. We'll actually have a little over $1,000 in the account. So 9 years it will take to, in essence, double our money, right? We start off with 500, and if we want to get to 1,000, that's doubling our money. It takes about 9 years to do it. Now we have another type of exponential function. It's the natural exponential function. And in fact, it happens so frequently that we gave it a special number, and we numbered that e. E is irrational like pi. You know, the 3.141529 blah, 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 blah. That's our pi that we use in dealing with circles and radius and diameter and circumference and area of circles. We use pi. That's very popular irrational number. E happens to be very functional in exponential functions, and E is approximately 2.7183. And in fact, if you do have a scientific calculator, and I'm looking at mine just to make sure mine does, and if I do it on scientific function, I do have it. Let me clear that out. So here's on my calculator, I have an e to the x. Okay, oops, sorry. I have an e to the x. So what I want to do is 1 e to the x. Oh, I got to do it the other way. Some calculators are one way. E to the x to the first power, and that will tell me a little bit more of what E is. It certainly doesn't tell me all of the digits of E because it's irrational, so the digits don't stop. But instead of just using 2.7183, which is what we're going to use, E goes along the lines of 2.71, 82, 81, 82, 85, so on and so forth. Okay. So E is incredibly helpful, especially with financial functions. Okay. So let's figure out what e to the x will look like. Now, if you remember the families of exponential functions, how it rose up like that, it started off really small and then it shot up to infinity. Because e is a positive number, right? It's almost 3, but not quite. It's more than 2, but less than 3. This is going to be that type of, it's going to be in that family. So we should have an idea of what the graph is going to look like. So here's what we do. I'm just going to plug in some values so I can graph this function. I'm going to select -2, -1, 0, 1, 2, 3, the ones that I like to use. I'm literally going to plug it into the calculator. If I did that, our function at -2 will be e to the -2. That's 1 over e to the second. And I could probably just plug that into my calculator here. E to the -2. Okay. I think that's how we do it. 1.35335. I'm just going to round it to 1.35. So that's how you put it into the calculator. The next one would be e to the -1. E to the, oops, clear that out first. E to the -1. That's going to give me approximately 3.68. E to the 0, well, e to the 0, clear it out first. E to the 0, it's going to be 1, right? It's a real number. So any real number to the 0th power is going to be 1. Okay. E to the first, well, that's how we figured out on my calculator what it looks like. There we go. So we're just going to round it to 7.72. Close enough. I mean, I can't graph the decimals, so I just need it close enough. E squared is going to be e squared. And e cubed is 20.085, so let's round it 20.09. All right. So here we go. Now I'm going to graph these values. -2 and 0.135 is about there. -1 and about 1/3. 0.36 is about 1/3, so I'm going to go about 1/3 of the way up. 0 and 1. I'm sorry, it's kind of crowded there. There we go. 0 and 1. 1 and 2.7, so that's nearly 3 but not quite. 2 and 7.3, so that's 7 and about 1/3. And then 3 and 20.09 is way up here. So I'm not going to connect that dot way up there, but you can see it is part of that family of exponential functions. So when I said that E was useful for financial functions, remember that compounding interest? Well, we have a formula that if we continuously compounded interest, meaning that every second of the day we're putting the money back, after that very first moment, after that very first second, you get a microscopic amount of interest added to your account. And then the next moment, it's just a microscopic, I mean, it grows extremely slowly. And then after a while, it grows fairly quickly. Right? It's an exponential function. So we actually have a formula, I like to call it PERT, P-E to the R-T, so P-E-R-T. Principal, E as in our special letter, to the R-T. This is how we're going to compound it continuously. So after T years, at a certain interest rate, we can figure out the amount of money that we have in an account if it is continuously compounded. Now, of course, in reality, it's not. But let's try and figure it out. Suppose we deposit that $500 in the account at 8%, and we do it for 5 years. So let's see. 5 years are $500. E to the 0.08, that's our interest rate, times our 5 years. All right, 0.08 times 5. So A in 5 years will be 500. E to the 0.4. Calculator. Let's get our calculator. Let's make sure I've got it on scientific calculator. So we have 500 times e to the 0.4. Voila. 745.91. So continuously compounded interest got us the same amount after 5 years as that big equation of AT equals P1 plus R over N T. That was our compounded quarterly, compounded for a specific period of time. We actually got the same amount. Kind of interesting, huh? Smaller equation, P-E-R-T, that's all you got to remember, but it was able to calculate the same thing as we did when it was compounded quarterly. Kind of cool. So that's it for this lecture. Until next time, be seeing you.